Now, fortunately, we are not gonna start with Turing's.
Fortunately, we're not going to start with Turing's 6 primitives.
6 primitives. This would be really painful programming.
Painful programming. Because they're down at the...
Because they are down at the level of take this value and
level of take this value and write it onto this tape.
Write it onto this tape. First of all, we don't have tapes anymore in computers, and even if we did, you don't
anymore in computers. And even if we did, you don't
wanna be programming at that level. What we're gonna to see with programming language is that we're gonna use higher level abstracts,
a
broader set of primitives, but nonetheless the same.
Set of primitives, but nonetheless the same fundamental thing.
Fundamental thing holds.
With those 6 primitives you can do it.
With those 6 primitives you can do it. Okay.
So where are we here?
So where are we here? What we are saying is in order to do computation, we wanna describe recipes. We wanna describe this sequence of steps built on some primitives, and we wanna describe the flow of control that goes through those sequence of steps as we carry on. So the last thing we need before we can start talking about real programming is we need to describe those recipes. Alright, and to describe the recipes, we are gonna want a language. We need to know not only what are the primitives, but
what are the primitives, but how do
we make things meaningful in that language. Language. There we go. All right. Now it turns out there are, I don't know, John, thousands of programming languages, at least hundreds of programming languages around. Professor John Guttega, unintelligible.
True. Thank you.
Thank you.
They all have.
They all have.
Their pluses and minuses.
Their pluses and minuses.
I have to admit,
I have to admit in my career here, I think I've taught in
career here, I think I've taught in
at least 3 languages. I suspect you've taught more.
languages. I suspect you've taught more, 5 or 6, John.
5 or 6, John.
Both of us have probably
Both of us have probably programmed in more than those
programmed in more than those number of languages. There's at least
number of languages, at least programmed that many, since we
that many since we taught in those languages.
taught in those languages.
One of the things you want to
One of the things you wanna realize is
realize is there is
no best language.
best language. At least I would argue.
At least I would argue that. I think John would agree.
I think John would agree. We might both agree.
We might both agree we have our own nominees for worst
We have our own nominees for worst language.
language. There are some of those.
There are some of those. There is no best
There is no best language.
language. Right?
They all are describing different things.
Describing different things.
Having said that some of them are better suited for some
some of them are better suited for some things than others.
things than others.
Anybody here?
Anybody here heard of MATLAB? Maybe programmed in MATLAB?
Heard of MATLAB?
MATLAB.
Programmed in MATLAB. It's great for doing things.
It's great for doing things with vectors and matrices and
Things with vectors and matrices and things that are easy.
things that are easily captured in that framework.
Easily captured in that framework. But there's some things that
But there's some things that are a real
are real pain to do in that.
pain to do in MATLAB.
So MATLAB,
So MATLAB's great for that kind of thing.
is great for that kind of thing. C is a great
C is a great language for programming things that
language for programming things that
control data networks, for example.
data networks, for example. I
happen to be, and John teases me about this
John teases me about this regularly.
regularly. I'm an old-time Lisp programmer, and that's
old-time Lisp programmer. That's
how I was trained.
And I happen to like
And I happen to like Lisp and Scheme. It's a great language
Lisp and Scheme. It's a great language when you're
trying to deal with problems where you have arbitrarily structured data sets. It's particularly good at that.
So
the point I want to make here is that there's no particularly best language. What we're gonna do is simply use a language that helps us understand. So in this course, the language we're gonna use is Python.
Python. Which is a pretty new language.
Which is a pretty new language. It's growing in
Which is growing in popularity.
popularity. It has a lot of the elements of some other
It has a lot of the elements of some other
languages because it's more recent. It inherits things
because it's more recent. It inherits things
from its progenitors, if you like.
Progenitors, if you like. But one of the things I want.
But one of the things I wanna stress is this course is
This course is
not about Python.
About Python. Strange statement.
Strange statement.
You do need to know.
You do need to know how to use it, but it's not about the
How to use it, but it's not about the details of where.
details of where do the semicolons go in Python.
Where do the semicolons go in Python?
All right.
Right?
It's about using it to think.
Using it to think.
And what you should take away from this course is having learned how to design recipes, how to structure recipes, how
to design recipes, how to structure recipes, how to do things.
To do things in modes in Python.
In modes in Python,
those same tools easily transfer to any other language.
Pick up another language.
You can pick up another language in a week, couple of weeks at most. Once you know how to do Python. Python. Okay. In order to talk about Python and languages, I want to do
Python and languages. I want to do one last thing.
One last thing to set the stage for what we're gonna do here. And that's to talk about the different dimensions of a language. And there's three I want to deal with. The first one is whether this is a high level or low level language. That basically says how close are you?
Says how close are you to the guts of the machine?
The guts of the machine.
A low-level language.
A low-level language, we used to call this assembly.
But you used to call this assembly
programming. You're down at the level of your primitives.
Down at the level of your primitives
are literally moving pieces of data from one location of memory to another through a very simple operation. A high-level language, the designer has created a much richer set of primitive things. In a high-level language, square root might simply be a primitive that you can use, rather than you having to go over and code it.
And there are trade-offs
and there are trade-offs between both.
Between both.
Second dimension is whether this is a general versus a
general versus a targeted language.
Targeted language.
By that I mean.
And by that I mean, do the set of primitives support a broad range of applications, or is it really aimed at a very specific set of applications? I'd argue that MATLAB is basically a targeted language. It's targeted at metrics and vectors and things like that. And the third one I wanna point out is whether this is an interpreted versus a compiled language.
Versus a compiled language.
Compiled language. What that basically says is the following. In an interpreted language, you take what's called the source code.
You take what's called the source code, the thing you write.
The thing you write, it may go through a simple checker, but
it may go through a simple checker, but
it basically goes to the interpreter, that thing inside.
Goes to the interpreter, that thing inside the machine that's going to...
The machine that's gonna control the flow of going...
Control the flow of going through each one of the instructions.
Through each one of the instructions. And give you an output. So the interpreter is simply operating directly on your code at run time. In a compiled language, you have an intermediate step in
language. You have an intermediate step in which you take the source.
Which you take the source code. It runs through what's
called a checker,
or a compiler, or both, and it creates what's
compiler or both, and it creates what's called object code.
Called object code.
And that does two things.
And that does two things. One, it helps catch bugs in your
things. One, it helps catch bugs in your
code. And secondly, it often converts it into a more efficient sequence of instructions before you actually go off and run it.
Right? And there's trade-offs between both.
I mean, an interpreted language is often easier to
interpreted language is often easier to
debug because you can still see your raw code there, but
you can still see your raw code there, but it's not always as fast.
It's not always as fast. A compiled language is usually much faster in terms of its execution.
Execution.
And it's one of the things you may wanna trade of.
You want to trade off. Right.
In the case of Python, it's a high-level language.
Python. It's a high-level language. I would argue. I think John would agree with me. It's John would agree with me. It's
basically a general purpose language. It happens to be better suited for manipulating strings than numbers, for example, but it's really a general purpose language, and it's primarily, I shouldn't say primarily, it is an interpreted language.
It is an interpreted language.
Okay?
As
a consequence, it's not as good as helping debug, but it
it's not as good at helping debug, but it
does let you, sorry, that's the wrong way of saying it's.
Sorry, it's the wrong way of saying it's not as good at catching.
Not as good at catching some things before you run them.
Some things before you run them, it is easier at some times.
Is easier at some times in debugging as you go.
Debugging as you go along on the fly.
Along on the fly.
Okay, so what does Python look like?
Okay, so what does Python look like? In order to talk about Python, actually I'm gonna do it this way. We need to talk about how to
write things in Python.
Write things in Python. Again, you have to let me back up slightly and set the stage.
Back up slightly and set the stage. Our
goal is to build recipes. You're all gonna be great chefs by the time. All right. Our goal is to take problems and break them down into these computational steps. The sequence of instructions that will allow us to capture that process. To do that, we need to describe not only what are the primitives, but how do we capture things legally in that language and interact with the computer.
And so for that we need a language.
We're about to start talking about the elements of the
language,
but to do that we also need to separate out one last piece of distinction. Just like with a natural language, we are gonna separate out syntax versus semantics.
syntax versus semantics. So what's syntax?
So what's syntax? Syntax basically says what are the legal expressions in...
He says, what are the legal expressions in this language?
This language. Boy, my handwriting is atrocious, isn't it?
My handwriting's atrocious, isn't it?
There's an English sequence of words.
English sequence of words. It's not syntactic.
It's not syntactically correct, right?
Completely correct, right? It's not a sentence.
It's not a sentence.
There's no verb in there.
There's no verb in there anywhere. It's just a sequence of nouns. Same thing in our languages.
In our languages,
we have to describe how do you put together legally formed expressions. Okay. And as we add constructs to the language, we are gonna talk about. Second thing we want to talk about very briefly as we go. Along is the semantics of the language. And here we are gonna break out two pieces: static semantics and full semantics. Static semantics basically says which programs are.
Semantics basically says which programs are meaningful. Which expressions make sense. Here's an English sentence. It's syntactically correct. Right? Noun phrase.
Noun phrase. Verb, noun phrase.
Is verb, noun phrase. I'm
not certain it's meaningful unless you are in.
It's meaningful unless you are in the habit
of giving your furniture personal names.
Personal names. What's the point?
What's the point?
Again, you can have
things that are syntactically legal.
Things that are syntactically legal
but not syntactically meaningful. And static semantics is gonna be a way of helping us decide what expressions, what pieces of code actually have real meaning to it. All right. The last piece of it is in addition to having static semantics, we have sort of full semantics. which is what does the program mean? Or said a different way, what's gonna happen when I run it?
That's the meaning of the
That's the meaning of the expression.
That's what you want.
That's what you want.
You want to know.
You want to know what's the meaning of this piece of code.
What's the meaning of this piece of code when I run it?
When I run it, what's gonna happen?
What's going to happen? That's what I want to do.
That's what I want to build. The reason for pulling this out is what you're gonna
pulling this out is what you're going to see.
See is that is most languages, and certainly in
most languages, and certainly in Python.
In Python, we got lots of help here. All right, Python comes.
We get lots of help here. Right? Python comes built in
with something that will check your static. Sorry?
It's something that will check your static. Sorry,
your syntax for you.
Syntax for you.
And in fact, as a sidebar, if you turn in a problem set that...
In fact, as a sidebar, if you turn in a problem set that
is not syntactically correct, there's a simple button that...
Syntactically correct. There's a simple button that you push.
You push that will check your syntax.
That will check your syntax. If you turn a program...
If you are turned in a program that's not syntactically...
It's not syntactically correct, the TAs...
Correct. The TAs give you a 0.
Give you a 0. Because it said you didn't even...
Because it said you didn't even take the time to make...
Take the time to make sure this syntax...
Sure, the syntax is correct.
Correct. The system will help you.
The system will help you find it. In Python, it'll find it. I think one bug at...
We'll find it, I think, one bug at a time, right, John?
At a time. Right, John?
Finds one syntax error at a time. So
it finds one syntax error at a time. So you have to be a...
You have to be a little patient to do it.
Little patient to do it. But you can check that
you can check that the syntax is right.
The syntax is right.